Hey guys, on this second video on oscillations, what I want you to pay attention to and jot down are the equations. Again, we're going to jump to tie-dye guy and the gal, and they're going to talk you through how do you do mathematical calculations. Important things to pay attention to is there's the term of frequency, period, and then the sinusoidal part. It's at frequency. All these kinds of things matter, and so make sure you jot down the equations so you can do the problems.
So in the last video, we looked at some of the basic concepts for oscillatory motion, and now we want to solve some problems. We're going to look at techniques for problem solving. And Brenda, you got a problem for us?
I do. So our problem is a 250-gram mass is suspended from a spring. Pulling the mass down by an additional 10 centimeters takes a force of 1 Newton. If the mass is then released, it will rise up and then come back down. At what time does the mass reach its maximum speed? What is the maximum speed?
And just to clarify too, we're talking about this little mass right
Yes.
here.
Yes, we
And
are.
if you pull it down by an additional 10 centimeters, it takes about 1 Newton. We measured this. So we're going to calculate when it reaches its maximum speed and what is that maximum speed. But first, we have to strategize. And my strategy is to say it's a mass on a spring. It's simple harmonic motion. So we got our strategy. We're going to treat this as simple harmonic motion. This is some preparation. And Brenda, let's characterize this motion. And I would draw a graph. Let's do this.
I think so. So since we said there's two things that kind of characterize an oscillation, those are frequency and amplitude. So I think I'm going to draw a position versus time graph. Brian, what do you think?
Okay, that sounds like a good way to kind of like wrap our minds around what's happening here.
And I put Y because we're talking about vertical position. And, well, we need to draw the motion. I know generally what it's going to look like. It's going to look like a sine curve. But where does it start?
Well, this one we pulled it down to make it get started. So yeah,
Oh,
starting
so
down
it's
there
gonna
is
be
looking
down
good. Looking
here.
good.
Actually, I started this way too low down here. So let's move it up a little bit. There we go. Start it here. And there we go.
All right.
So that's generally what it looks like.
Pretty signy
I think
right there.
so.
And then if we want to fully characterize this graph, we're going to have to put some numbers on these axes.
Oh,
so
yeah.
one thing is we're going to have to know what is the amplitude. The amplitude is the distance from equilibrium. Oh, but wait a minute. We were told some information in the problem statement. I think you folks can figure out what the amplitude is.
I think so too. So what is the amplitude? We'll give you some choices. All right, so in the problem it says we're pulling this spring, this mass on a spring, down 10 centimeters from equilibrium. So I'm thinking that our amplitude is just going to be 0.10 meters. It's negative down here and positive up here.
Oh, right, because it's 0.10 meters from the equilibrium position.
From equilibrium.
And so that is going to be our amplitude.
Yes.
So I'm just going to record that
Yes.
over here. So amplitude is 0.10 meters. Now the other thing we need, that gives us our position axis, but we don't have anything on our time axis yet.
We need our period.
A period.
Yeah.
If you have one full cycle,
Which is from here to here. We need to find what our period is.
that is going to be the period.
Yes.
So how are we going to find the period? What do we need to know?
Well, we're given a general equation for mass on a spring to solve for period, and we can see here that the period, which is t, is equal to 2 pi times the square root of m over k. M being the mass, k being the spring constant. And we don't have the spring constant, but I think we can find it because we know that the restoring force, or the spring force, is equal to the spring constant times the stretch of the spring. So,
Oh yeah, and in the problem statement, we were told that you stretched it a certain amount and that produced a certain force.
yes. So we can use those things to solve for k, but I want y'all to do that.
Oh yeah, when you say we mean you, to be clear.
You're doing the work. So, what's the spring constant? We'll give you some choices. All right, so I'm told in the problem that our spring force is 1 Newton. And we're told that, well, our distance from equilibrium is, what, Brian?
0.1 meters.
0.10 meters, because it's the amplitude. So if I do some rearranging and calculate it out, I get a spring constant of around 10 newtons per meter.
Awesome. And with the spring constant in hand, if this is 10 newtons per meter. And I know the mass, too. This is a 250 gram mass, or 0.25 kilogram mass.
By golly, we can solve for the period.
We can solve for the period. And if we do that, I get a period of 1.0 seconds.
Well, that's a lot of work for 1 second.
I know, but we're not scared of a little hard work.
No,
Brenna.
we're not.
We're not scared of that.
No.
So with that, you can put some numbers on the axes.
That
And let's
I
go ahead
can.
and mark some of the crucial times in this particular
I think
motion.
So we know that one full oscillation is going to take 1 second. So I'm going to put 1 second right here. We know half an oscillation is going to take half a second. And in these in-between parts, that's
those
about
are important
a
points.
quarter.
It's going through equilibrium.
Yeah.
That's important.
So I'm going to say that this one is equal to 0.25 seconds, and it here is 0.75 seconds.
Perfect. And now we have this graph to help us wrap our minds around what's happening. We have some
We have
times on
times.
here.
Yeah.
And the first thing that people were asked was, at what is the first time that the mass reaches its maximum speed?
Well, if we have a position versus time graph, I think we can figure out where the max speed occurs.
I think we can throw it out to them.
I think we can. So what is the first time that the mass on a spring reaches its max speed? We'll give you some choices. So on this graph, we have position versus time. Well, I know that velocity is equal to a change in position over a change in time. Oh, so
on a graph of y versus t, this is basically a slope.
yes, and this is going to be greatest when the slope is the greatest.
It looks like here I got a slope of 0, basically. Here I got a
Yes.
slope of 0, so it's not moving
Yes.
at those points.
But right here, it looks really slopey to me.
It does.
And so I'm going to say that at this point right here, 0.25 seconds is when we hit our max.
So right
speed.
there, right when it's going through its equilibrium position the first
Yes.
time, that's when it reaches its maximum speed.
Yes. But now we need to know what the max speed
yeah,
is.
we didn't know what the max speed is, so for that, we're going to need another relationship. And if we know the frequency and we know the amplitude, we can calculate the maximum velocity. It's 2 pi times the frequency times the amplitude. That's our basic relationship for the maximum velocity.
But Brian, we don't have frequency.
We don't have frequency, but we do have period. And I know frequency is just equal to 1 over the period.
Oh, well,
So-
that's just equal to 1.
That's just equal to 1. If the period is 1 second, the frequency is 1 hertz, or 1 cycle per second. And if I take that and put it in for the frequency, and the amplitude we already know is 0.10 meters, that gives me a maximum speed of 0.63 meters per second. So it first reaches its maximum speed at 0.25 seconds, and the speed that it reaches is 0.63 meters per second.
Interesting, but we can't just say that. We have to assess it, Brian. So go ahead and pick up my little friend here again.
All right.
And if I pull it approximately 10 centimeters from equilibrium, we're going to kind of count the period, and
Period's about 1
I would say it's about 1
second.
second. And it's really slow, which
0.63 meters per second. It's pretty chill.
slow. So I think this seems about right.
Seems to match my expectations. That's perfect.